All right, so today we're going to take a look at a different topic. It's the topic of area. And in particular, we're going to look at some notation that you might not have seen before, or if you have, it might have been a while since you've seen it, enough that you really don't remember much of it at all. That notation is called sigma notation. So sigma notation is a notation that talks about adding things up, summations. So the sum of n terms, a1, a2, a3, all the way up to an, is written as, so that giant sigma at the beginning is summation. It tells you what value you start at. Whoops, that was supposed to be a highlighter. And this one's 1. And what value you end at. And it's telling you to add a bunch of them together with those subscripts. So on the right-hand side, you see it written out sort of long ways. It's a1 plus a2 plus a3 all the way to a sub n. On the left-hand side, you see it in a compact form. The I is called the index of summation. A sub I is the ith term. And then the upper and lower bounds on the summation are the lower underneath the sigma notation, which is 1, and the upper one above it, which is n. And when we're working, we're going to have that n on top be a specific number, right? So it's not going to say 1 to n, it'll say like 1 to 5, and we're adding up the first 5 terms. For those of you who at some point will be going on to Calc 3, and there are a few of you, you will actually see that n on top eventually become infinity. And then there's other nuances to what happens after that. So that's a Calc 3 exciting thing to look forward to. So let's talk about finding the sum and how this works in general, though. So we only have one example like this because once you've done it, you're going to know how to do it. This is not a complicated process. It's all basic arithmetic. It's not calculus. The new part for this for you probably is simply the notation. This is telling us that we're going to add up the first 6 terms from 1 to 6. And it's telling you what the equation, basically, it's an expression, what it is in terms of I. And so what we're really going to do is we're really going to write down what is A1, A2, A3, all the way up to A6. And then we're going to add them up. That's all it is. Okay? So if I put the number 1 into 3 times 1 minus 2, what do I get? 1. How about the number 2? 4. How about the number 3? 7. How about the number 4? 10. Okay, so I want you to pause just a second to recognize something. We can keep putting it in, and that's fine, and you guys are doing it super fast. But do you see a pattern in what's going on with the numbers? Yeah. We're adding 3 every time. Do you guys see it? Okay, so that's happening because this is multiplication by 3. 3 is the slope. Okay, so if you recognize the pattern happening, you can just continue the pattern instead of actually evaluating into the expression. Either way, it will work. We're going to add these together. If you want to add them in your head, you can. If you want to add it, grab a calculator and add them. You're not going to have something that has like 50 values. That's not going to happen. But you could have up to, I think 16 is the most that shows up in WebAssign on any of the problems I selected. Don't hold me to that, but that's what I remember. So what happens when we add 1 plus 4 plus 7 all the way to 16? 51 is it. Okay, easy peasy, right? Just doing some basic arithmetic. That doesn't mean that your function's always going to be linear. It doesn't always end up being 3i minus 2. It could have other pieces to it. But the kicker is there's actually shortcuts to doing this as well, that if you did have, say, 50 terms, you certainly would not want to do this 50 times and then add that together. So that's actually what we're looking at next. We're looking at some generalized formulas for what happens when we're adding these terms together. The first one is a constant. So if n is a positive integer and you're doing a constant, so let's just say that this had said 5, right? So if this said the summation from I equal 1 to, we'll do 10 of 5, well, there's no I to put the numbers into, right? So they're all just going to be 5. A whole bunch of 5s. How many 5s? 10 of them, because it tells you we're going to start at 1 and we're going to go to 10. There's going to be 5 plus all the way up, still 5, and there's going to happen there 10 times. That's what happens when you have a constant. And actually, that's what's happening here at the end with your negative 2. There's a constant at the end of it that could be broken apart. So what happens? Well, what really happens is you just take that number, mine was 5, and you multiply it by the number of terms. however many there are. So it's C times N. You don't have to calculate anything. You don't have to write anything out. It's just C, whatever the constant is, times the number of terms. The next one's the linear one, okay? So this actually was a linear equation. I know it has a 3 in front of it, but you have the I showing up there just like this one is otherwise. And so what you're really doing here is you're adding up the numbers 1, 2, 3, all the way until you get to whatever you end with, and we'll end with 100 just for a moment. Because I want to show you that this one's really simple to see where it comes from, but you might not have ever seen it before. And since I teach it to my elementary school teachers and they can do it just fine, I know you guys are going to like it too. Okay? So this is some sort of number. And the more numbers you have, the less friendly it is to actually add them all up. Agreed? Okay, so this is actually credited to a mathematician named Gauss. Gauss's first grade teacher. This is the story that is associated with it. I don't know if it's 100% true, but this is the story. Gauss's first grade teacher gave them an assignment to keep them busy. I'm sure your teachers have never done that before, right? They wanted them to add the numbers from 1 to 100 together, and I don't know about you, but if I were working with first graders, that should take them a while. That would keep them busy. And it wouldn't be absolutely terrible, right? Like, it's practical, useful, like they're learning to add. Okay, cool. Well, Gauss did a little bit of manipulation. He's a very important mathematician. And here's what he basically did. He said, okay, well, notice that if I add these numbers backwards, so 100, 99, all the way down to 1, that every single one of these adds up to the number 101. Did you notice that? Okay. Well, that's double what I did to start with because I added this to itself, right? So this is S, this is equal to 2S. I am sure that he did not have all the same notation that we did in regard to this. Well, what happens when we add 101 to itself a whole bunch of times? Well, it looks an awful like what we did right here, right? So it should be that 101 added it to itself however many times we did it, and we did it 100 times because there's 100 numbers. And then we divide by 2 to eliminate the double counting because I added it to itself. Okay? So he did some version of that at 6 years old. Yeah, so you can all feel a little bit behind the curve today because of Gauss. But the cool thing about this is that there's nothing special about the fact that I started at 1 and I ended at 100. You can start wherever you want, you can end wherever you want, and this process still works. So what is it that's actually happening? Well, what's actually happening is that whatever the n value is here, you take that and you multiply it by n plus 1, sorry, not minus 1, plus 1. Right, so there's where you see that 100 and that 101 coming out. That was my number of terms, and my number of terms plus 1. And you divide it by 2. So that's where this is actually coming from, is from this kind of a process. Okay? When we get to the test, you're going to have these memorized. They're not hard. You guys are good at memorizing, especially formulas, right? Y'all don't like memorizing paragraphs of things, I get that. But this is not too bad. There's only two more to memorize. The next one's quite similar. I'm not going to justify the next two out. I'm just going to give them to you. I don't actually know the history behind each of those. I do know the history behind the Gauss one, so I think it's an interesting one. But the third one here, the I squared, looks very similar in its nature to the beginning of the last one. So you actually take n times n plus 1, and then you multiply it by 2n plus 1, and you divide by 6. Okay, so this is what happens when we sum the I squared. So I squared means that I'd be summing 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared and so on all the way up to wherever I'm supposed to be ending the problem. And the last one, the cubed one, again, is very similar feeling. I've got n squared times n plus 1 squared, and it divides by 4. So in a very real sense, it takes I and it squares everything. Do you see the pattern there? Square each of the individual factored pieces, and I get I cubed. So why is that useful? Well, it's useful because if we did have a whole bunch of numbers, we wouldn't have to calculate it. Now, my next example, it only has 16. So you could actually do it out, and it wouldn't be the worst day in the world if you had to do 16 items. But I contend that if I had you go from 4 to 140, it might be the worst day in the world. It might. Right? I don't want to do this 136 times, do you? No. So let's practice it with the smaller values first so you can just see how it works, and then we'll look at the values where they're larger. All right, so what we're going to do is we're going to do like what we did with limits, where we separate out all the pieces so that I could utilize these properties. So notice I want them to all look like one of these four. Everything has to match one of these four exactly. And we have all the properties that you would hope and want to be true. Namely, I have 5i. Well, I can pull the 5 out in front, and I can do my summation from I equal 1 to 16 of the I. That's a terrible I. That's better. And then I can do my summation with the 4 right here from I equals 1 to 16 like this. So I can separate them out. I got a constant multiplier pulled out in front, just like I did with derivatives and with limits and with antiderivatives. It's the same process on all of them, right? Pull the constant multiplier out. Separate addition and subtraction, just like I separate addition and subtraction with all of those different kinds of operations we've looked at. And then what happens is that this and this look just like one of these with a 16 on top, don't they? So the number on top, namely n, is now 16. So the 5 stays in front. The I one says that I'm supposed to do n, which is 16, times n plus 1, which would be 17, divided by 2. And I'm going to subtract. The second one that's circled is actually the first property here. It's a constant. It's the number 4. So I've got 4 times n, which is 16. You do not have to find 16 individual things. I use some arithmetic to do so instead with simpler pieces. So we multiply 5 times 16 times 17 divided by 2, and 4 times 16. And what do we end up with? 616. Thank you, Lainey. 616. Okay, did everybody get 616? I only saw a couple of you calculating.
Oh,
Yep.
why don't you have to apply the summation to the 5 as well whenever you write it?
Because it's multiplied. It's not added. The 5 is being multiplied. Right, exactly. It's being multiplied. I could have left it inside if you wish, but it's just being multiplied, so pulling it to the front to ignore that piece matches up a little bit cleaner to these pieces.
I got why you separated, but I was like,
Yeah.
confused in my head.
Yep,
So
that's
the
why.
Does that mean we're going from 4 to 16, or what is the I?
So our problem went from 1 to 16. Okay, and all of these formulas won't go from 1 to n.
Oh, that was a 1.
Yeah, it was a 1. The next one's a 4. The next one's 4. Yeah. So we are going to have to talk about what happens on the next one here, because, there's a 4 on the bottom instead of a 1, and that does change things. So there's a couple things to keep in mind. First of all, this feels a little bit awkward, but I put it in here on purpose. Do you notice that they're using the n here instead of the I?
Yeah.
Yeah. And it's a little frustrating because we have all of these based on the letter n being the top value. Agreed?
Yeah.
So my suggestion when that happens, because they use all the letters interchangeably inside of WebAssign, inside of your textbook or whatever, is to just change them into I's to eliminate the confusion. Okay, for the purposes of what you're doing, for the purposes of putting into WebAssign, you're not going to be putting it into WebAssign anyway. It's just a dummy variable. So for what we're going to do first, I'm just going to rewrite this with I's so that it matches the form of what we did before. Okay, so I'm going to ignore the fact that this starts at 4 for the moment and pretend like it starts at 1. Okay, we'll come back to what we do because of the first part in a minute, but we're just going to ignore it for the moment. I do need to multiply this out as well. So if I multiply out I times I minus 1, what will I have? I squared minus I. Okay, so the first thing I'm going to do down here is I'm going to do my summation. I am going to let my I start at 1 for the moment and go up to 140. And we're going to do I squared, and then we're going to separate it out, and we have our summation from I equal 1 to 140 of I. I promise we will figure out what to do with the 1, 2, and 3 that's missing from I equals 1, I equals 2, I equals 3. But these pieces look just like these formulas over here now, right? The first one, I squared, is the third formula. It says I multiply n times n plus 1 times 2n plus 1. So n is 140 times n plus 1, which is 141. And then 2n, which would be 280 plus 1, so 281, divided by 6. The second one, I'm plugging the number 140 into equation number 2. So 140 times 141 divided by 2. Okay, everybody good so far? Excellent. Your calculator will give you some values here. I don't have the individual pieces written out for the parts that we've done.
Do you want the first one?
Sure.
924,400.
Thank you. And then 140 times 141 divided by 2. It'll be much smaller, I think.
9,940.5.
It can't be 0.5.
Oh, I did 141 this time.
It's okay. Try again. It has to be whole numbers as we're doing this, since
Yeah.
we're...
9,870.
Okay. Okay, anybody else who was calculating, did your numbers show up the same way? Yours did, Abby? Okay, cool. All right, so here's the deal. I mean, I can subtract these, and we will in just a second. But since I changed my starting spot to be starting at 1, when it should have been starting at 4, I included an a sub 1 value that I shouldn't have. I included an a sub 2 value that I shouldn't have, and I included an a sub 3 value that I shouldn't have, right? So any guesses as to what I might need to do to compensate?
I equals 1 and you go to 3 and then you subtract that.
Yes, but it's easier even than what you just described.
You plug all of those in and then you subtract it.
Yeah. So what I'm going to do is I'm simply going to subtract off the A1 and the A2 and the A3. Because it's simple enough to plug the number 1 in, to plug the number 2 in, and to plug the number 3 in, right? It is. The equation I'm plugging them into is the I squared minus 1. So I'm going to go back and I'm going to compensate along the way here. So over here now, what I've actually done by subtracting them is I've changed this, so it really is starting at I equal 4. I'll call it a sub I, so I don't have to write it out again, to 140. Because I've subtracted off the A1, A2, A3 after I started it back at 1 instead of starting it at 4. So if I plug the number 1 into I squared minus I, what do I get? 0. It's a lovely one. What if I plug in the number 2?
3.
I get 3. And if I plug in the number 3, I get 8. Everybody good with that? I think it's 6. I think you actually added them together maybe. 3 should be 3 squared, which should be 9 minus, should be 6. Okay, is that okay?
You said you plug in 2. You get 2.
Yes,
Squared minus
yes. I was just taking y'all's numbers. I don't have them written out individually. I have the combined total at the end. I'm like, the combined total is not working. Something's wrong. 2 and 6, that's better. Awesome. So then this is minus 8 if you want to combine these pieces at the end. So we need 924,490 minus 9870 minus 8. And that should be 914, 612. So that's what happens when it doesn't start at 1. All right, so where is this leading? Well, it's actually leading into a connecting point for antiderivatives. And we haven't talked about that connecting point, but we're going to start that point today. We won't finish it in this section today, but we will start it. We spoke back on the very first day of class about an application of calculus where we were trying to find the area under a curve. We talked about the fact that we can find the area of certain discrete shapes like squares and rectangles and triangles and trapezoids and circles and stuff like that using formulas from geometry. But if we have these sort of arbitrary shapes like this one here, and I wanted to find the area, say, between here and here in this arbitrary shape, I need calculus because the shape is not one of the ones from geometry that I can actually break apart perfectly. So this is what I'm going to be looking at. I'm going to be looking at finding this shaded area. So the area of this region can be approximated by rectangles. There are 3 different approaches that we're going to do. There's more than that because there's other shapes you can use as well. We're going to focus on rectangles. There are 3 different approaches to determine the height of the rectangles. So generally speaking, what we're going to do is we're going to take the interval and we're going to divide it into pieces, even pieces. So like if we divided it into halves, it would be looking like this, right? The interval along the bottom, divided it approximately in half. And the picture works pretty nicely for me to draw it for fourths, so that's the picture I'm going to draw. There's nothing special about the number 4, it just draws nicely. So if I were to divide this into 4 different rectangles, I would make my heights something like this, okay, like vertical pieces. And then we have to decide, right, we got the widths, right? My width is whatever this distance is, and they should all be the same. Those are all good. We have to decide which of those sides heights, or what height we're going to use to make the area of the rectangle. So there's 3 ways to do it. I'll draw full pictures later, but let me just sketch 3 options here. One option is to let the left-hand point be the height. But you can see on this particular piece that if I do that, I'm going to find an area that's slightly too big, right? Option number 2, we're going to let the right-hand side be the height. All right, so that we're calculating this rectangle right here. And you can see if I do that, then I'm somehow minimizing, right? I don't have enough area to compensate. The third option, and it's typically the best, though it's not always the case, but typically, is to take the midpoint and then to use its height. And so on that one, you might think, well, that looks pretty close, at least for the piece I've drawn, because it's overcompensating on part of it and it's undercompensating on the other part, right? So maybe it's sort of balancing things out, and that's the approach that uses the midpoint. So those are the 3 approaches that we're going to use. So let's actually write and draw them out, and you can see what happens from that perspective. So if we're using our left end points as the height, then we make each of them like I did before. So we're going to draw them in. And again, I'm going to draw 4 rectangles just because it's easy to draw, but sometimes you're going to be drawing more, or you could be drawing fewer. I don't think they have you draw fewer, but you could be drawing more. And you're drawing these heights of those rectangles, and then, or at least the vertical pieces. And then we're using the left-hand endpoint. So if we're using the left-hand endpoints, it looks like this. It's always the left-hand endpoint of whatever region we're looking at. And you can actually see that on the shape that I've chosen, it's not necessarily a bad estimate. And the reason is because on the first 2 rectangles, I'm overcompensating. But on the second 2 rectangles, I'm undercompensating. You see that? Now, that just depends on the shape that you're using as to whether or not that happens. This time, that happened. Partial overcompensation, partial undercompensation. So let's actually talk about what the area of this is. So we're going to call it L of x just because it's the left-hand endpoint. I would make your L curly so that at least it doesn't look like a 1. And we're going to call this endpoint over here x0. This will be x1, x2, x3, and x4. And the difference between these values, and I don't care which one I mark, I'll mark this one, is delta x. It's just a change in the x values. So every rectangle is calculated by doing length times width, right? Yeah. So my length times my width. Well, the width of each rectangle, delta x, and then the height, or whatever, the width, I don't know if I've said them in the right way, but the other dimension has to be calculated based on how far up I've gone, right? So this piece here is the delta x piece, and now I need to figure out how tall this rectangle is. Well, it's based upon this point right here that I used as my height point. And the way that that's calculated is you take the x value and you plug it into your function, so it's f of x0. Right, whatever that x value is, you plug it into your equation that you have, and you have the height. And then we go to our second rectangle. Well, it's still got a width of delta x, but how is its height now determined? F of x1. And what would I do for the next one? Well, it's delta x, and it's f of x 2. And then the last one is another delta x, and it's f of x 3. Notice f of x 4 doesn't end up being used. That corner did not get used because it's not a left endpoint. But here's the interesting thing about this that makes it easier to work with is, do you see there's a delta x factor in every single one of those terms? So instead of making 4 different multiplication calculations, what you can do is you can actually add together the 4 y values, f of x0, f of x1, f of x2, and f of x3. All right, you can add those 3 values together, and then you can multiply by the width one time, because they're all being multiplied by the same width. And this process repeats itself exactly, and this form repeats itself exactly when we look at right-hand endpoints. So over here with my right-hand endpoints, my picture looks a little bit different. I'm splitting it into the 4 pieces, again, for visualization purposes of what we're have happening. But I'm using the right-hand endpoints now. So the right-hand endpoints, I'm just going to start from the right because it makes it a little bit easier to think about it. And then I use the next rectangle to the right, and I use the 3rd rectangle, and then I use my 4th rectangle. And my labels are the same, x0, x1, x2, x3, and x4. But the 4 heights that I use are not fx0 to f of x3. They're shifted, right? The 4 heights that I use are these 4, f of x1 to f of x4. So when I'm looking at my right-hand heights, I've got that same delta x, but now I have f of x1, f of x2, f of x3, whoops, sorry about that, and f of x4. And that's where I would end the summation of the heights. Now I want to show you the connection back to what we did before, because I've written them both out. Over here, I don't have any space. I'm just going to have to move down here. This is a summation. It's from I equals 0 this time to 3 of delta x times f of x sub I. That's why this stuff's showing up in this section, is this is a summation of values, just like those summations that we did before. And the same thing's true over here. But this one starts at I equal 1, and it goes to 4 of delta x times f of x sub I. Yes, ma'am?
Is there significance to use x0, not x1 first?
It doesn't make any difference. It's just the notation that you generally see used as you started x0 and you ended x wherever you're ending. And this one I chose
So if
4.
it was x1, it would be fine.
Yeah, it would be fine. It wouldn't make any difference. It's just a notation thing for the purposes of us discussing it. The last one, the midpoint one. Let me draw it in. There's no formulas to write down, so it's a little quicker. We've already talked about basically what it does. We're going to split it into 4 rectangles. And it's a little bit more complicated to calculate because I need these midpoint locations. So I have to take the halfway points. And then they're my heights. And so my shaded in parts are these rectangles that are going down. Some of them overcompensating or undercompensating a little bit more than the opposite piece. They all have a little bit of that going on because of the particular type of equation that we're working with. But it's the height of the rectangle is the midpoint instead. Okay, so I have one example, because once you see one, you'll be fine. But I know that I can't hold you over right now because you guys have places to get to. So I'm going to do what I did before. I'm going to pause the video. I'm going to do the one example. It's probably going to take like 5 minutes, okay? So come back after class, after chapel, whatever you have going on next. Watch the last 5 minutes, and then you'll be good to go for Friday, okay? Okay, so we have one example we're going to do. Truly, they all work the same way. And I'm going to do an example of each of the types, the left-hand endpoint, the right-hand endpoint, and the midpoint. And I'm going to do one with 4 rectangles. Again, just because it's easy to work with. To be honest, you don't really need the whole graph to be able to do this, but it's often helpful to have the number line. So when I draw these, I just draw out the number line to give myself a reference point. So my number line here says that I'm supposed to be going through the interval from 0 to 2. And then here it tells me how many rectangles I'm supposed to have. It is 4. So I'm going to subdivide this into 4 pieces. If it said 8, I'd just subdivide it into 8, right? If it said 6, we would divide it in half, and then we divide it into thirds. So you can divide it into however many pieces it indicates in the problem that you need to. Here, it's telling us fourths. Once you've divided into however many pieces you're supposed to, you're going to find the actual x values between 0 and 2 that this actually subdivides into. Again, this one's very nice and clean. Some of yours might not be quite so clean, but you're halving it, right? So halfway between 0 and 2 on this one is the value for 1. Halfway between 0 and 1 would be 1/2. Fractions or decimals are fine. And then halfway between 1 and 2 would be 1.5, or I'm going to use 3/2. So as I'm working with part A, I'm going to call it part A, part B, part C. So we're going to call left-hand endpoints L of x. Oh, one thing I didn't write down over here. Midpoints, I'm actually going to call it M of x when we do the midpoint rectangles. So when we get to that for the part C, if you will, over here, that's what I'll call it. So we actually can look and we can calculate, right? So it is delta x. It's just the distance between our x values. So in this case, it's 1/2. So my distance is 1/2, and it's the same distance whether I use the left-hand endpoints, the right-hand endpoints, or the midpoints. So it's a distance of 1/2 between my rectangle, or on my rectangle widths. And then if I'm using my left-hand endpoints, I use the first 4 starting at the left. So I will use f of 0 plus f of 1/2 plus f of 1 plus f of, actually 3/2. Let me shift it over just a tiny bit to get myself a little more space. Your calculator can make those calculations. If you will ask me next time, I'll be happy to show you some cool calculator tricks for simplifying how to do those calculations in your calculator, in case you haven't seen those before. But your calculator can actually find f of 0, right? I know you can too by looking at this particular one. It's 5, right? It's not very exciting. But the calculations for the fractions might be a little bit messier and so forth. As we put this into our calculator, calculate the pieces, it ends up being 13.5. Now, the cool thing is, if you've utilized your calculator to do this, and here's how you actually do it. I can actually walk you through verbally, and then I can show it to you next class period. The way that we get these things to show up in your calculator is you can store the equation in y1. So your y1 is equal to 2x squared plus 5. And then back in your regular screen, I wouldn't put the 1/2 part in yet. I'd just put the other pieces in. And I would tell it y1 of 0, and then I would put in plus y1 of 0.5, and I would go all the way, right, up to y1 of 1, that's supposed to be y1, and then plus the y1 of 1.5, or 3/2. Remember, you can get the y1 by hitting vars, y vars function y1. That's how we did that. And then after I did that calculation where it summed it, then I would hit divide by 2, or times 1/2. The nice thing is that if you've done it that way, then for r of x, you can actually utilize that very nicely. So I still have 1/2, but now my endpoints start at 2, and they go backwards, the 4 from the right-hand side. So I actually start at f of 1/2. I do f of 1. F of 1.5 or 3/2, either way, and f of 2. So if you put this in your calculator, what you can do is you can hit second and enter, and it will pull up the previous line of work that you did. And if it's 2 steps back, you just hit second enter again, and it pulls it up. If you have the ability to pull it up, you can just change this f of 0 that we had right here, and instead you can replace it with f of 2, because that's the only difference. These pieces are all exactly the same on those 2 summations. So you can put that in, let your calculator do all the arithmetic part of it, and when it adds it together on this one, you get 17.5. Now, I mentioned before, and it is still definitely true, that the more complicated piece is actually the midpoint piece, and it is because the numbers end up being more challenging to work with, maybe, I guess. So let me take a look with you at what we do for our midpoint piece. So for part C, for midpoint, I still have the same width of my rectangle. It's 1/2. Okay, all the rectangles are 1/2. But now I need the pieces that are in between. So I need something in between 0 and 1/2. Well, that's 1/4. Between 1/2 and 1, that's 3/4. Again, you can use fractions or decimals, so if you would prefer to do that, that's fine. Between 1 and 3/4 is 5/4. And then between 3/2 and 2 is 7/4. So those are the numbers. I'll put them in decimal form here as well in case you like that better. So this would be f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. Let me shift this over. And again, the reason that this is also less friendly is because I can't utilize, the previous entry in the calculator like I did between parts A and parts B. I have to actually enter it by hand again. So I'm entering in y1 of 0.25 plus y1 of 0.75 plus y1 of 1.25 plus y1 of 1.75. Hit enter and divide by 2. And if I do, I'm going to get 15.25. Now, generally speaking, we do end up with one of these being low, one of them being high, and one of them being, namely the last one, the midpoint one being somewhere in between the two values. So that's a typical thing for us to see happen. The more numbers you have to do, like the more rectangles, the more tedious it is, truly, right? Because you have more things to add together. But your calculator is very good at being able to calculate those pieces. If you want to come see me in my office, I can show you, or I can just start out with it at the very beginning of class next time just so you can see it happen on my screen.